Thank you very much. Good afternoon, everybody. And first, I would like to thank, on behalf of our collaboration, the Simons Foundation, for giving us the funding to pursue this research and also organizing this fantastic workshop that I think everybody has enjoyed enormously. So quantum geometry is one of the themes in our research program. And I think there we have to now soon go from basics, at least towards real materials. And this is the theme of my talk. So since there might be some people who are not so familiar with this topic, I will give the basics, review of the basics in the beginning, how quantum geometry is related to superconductivity. Then I give like a one slide advertisement about things from my group that I will not talk about, but some might be interested to have a look at the paper later. Then comes the real stuff. These are both new topics that I haven't talked before. First, what happens with disorder, and then towards really real materials with quantum geometry. So let's go do the basics. Quantum geometry is an old topic, started maybe in the 90s or something, in the context of DFT and making some nicely localized one-year functions and so on. It spread to quantum information and so on. But there were some works around, let's say, 2013, 14, and 15 hour superfluid weight and so on, that raised interest that this concept could be useful in condensed matter physics in general. And after that, as you see, it has really exploded to various directions. And this red means that I have worked on those topics, and there are review articles I can recommend if you are interested in this thing. So get the basic definition, right? So quantum geometry here in this context means distances between quantum states. You could have a generic quantum state. You take a small parameter change. You ask, can I express it like with the metric times the change? And yes, you can. There is an object called a quantum geometric tensor, which contains derivatives of your wave function with the parameter. And its real part is the metric, like this. And the imaginary part is very curvature, so quantum geometry is like the bigger context under which topology is naturally located. And for concreteness, this U could be a Bloch function and K, the lattice momentum, but this is completely generic. And now, this is interesting in context of superconductivity in general, but especially in flat band superconductivity. So if you take a band that is quite flat, so interaction is bigger than the bandwidth, and compare to the dispersive band, by the way, this is the Bloch function, and this is periodic part of the Bloch function will be a very important part of my talk. Then you see that actually BCS theory already gives you a result that TC is proportional to the U only. So because interaction is the only energy scale here, kinetic energy is 0, and this is volume of the flat band. So this is sort of promising because at small u, it's exponentially better than the usual BCS result. So maybe if you manage to get attractive interaction in your band, in a flat band, maybe it gives you really high TC. But this TC here tells only about the absolute magnitude of the order parameter. And order parameter is, of course, more. And you have to also evaluate the Meissner effect, C Meissner effect. And for that, you have to evaluate the superfluid density or stiffness, which in its simplest form is Cooper pair density divided by the effective mass of the electron. And that one is 0 in a flat band because it comes from the dispersion. So that looks like the end of the story. Flat bands are not good. But this is not the whole picture, because often the interesting flat bands emerge in a multiband context due to some interference effects. So you have to do multiband theory. And from there, we showed in this 2015 paper and a follow-up that superfluid weight actually has two parts: the conventional one, the one that would be zero at flat band, and then another part which is non-zero only in multiband context, and it can be non-zero in a flat band. So this rescues flat band superconductivity. And it's geometric. We named it geometric because one can show that it relies on quantum geometry concepts, and in certain limits the connection is even very explicit. So if you take this limit of isolated flat band, interaction bigger than bandwidth and smaller than the band gap to the next band, and furthermore you assume so-called uniform pairing condition, so that the order parameter is same in all orbitals where it's non-zero. And this is not so exotic as you might think, because it has been shown that this condition is valid whenever your orbitals are related by symmetry. So that could actually happen even in a real material. In that limit, you can show that the geometric part of the superfluid weight is proportional to the density, nu, 1 minus nu, number of orbitals, interaction, linear dependence on interaction, just like TC, and an object that is the quantum metric integrated over the Brillouin zone. And there is also important part here is the minimal quantum metric. So actually, quantum metric Berry curvature and so on, they depend on the positions of the orbitals. So orbital embedding in other language. This is shown in this paper, and in this this paper here, we show that actually one needs to have this minimal quantum metric to make the whole thing orbital position independent. I mean, in the original paper we had the same formula but without this min. Right. So the quantum geometric contribution is there. What does it really mean? I mean, why is it there? Some kind of intuition. So I usually show this this cartoon that if you would have a trivial flat band, some kind of wave functions or one-year functions localized into atomic orbital, so atomic limit, then if you add interactions, pretty much nothing happens. But in these interesting multiband flat bands, which are caused by interference, you might have overlapping one-year functions. And then with interactions, you get some movement. And we actually showed in this paper that we projected to the flat band and showed that the movement of the Cooper pairs indeed depends on the one-year function overlap. And this then makes this connection to quantum geometry also more understandable, because it's known that quantum geometry and even topology controls how well localized your one-year functions can be. And this, when we could derive this kind of bound that if you have attractive interactions, then in a flat band you should have superconductivity if you have either non-zero Chern number or the quantum metric at least. Good. Yes. And and after we have done the basic work, twisted bilayer graphene came, and people were suddenly very interested in flat bands. So our group and me and Tero and so on, and then two other groups suggested that this could be important for twisted bilayer graphene. And now there are two experiments where they observed or measured the superfluid weight, either directly or indirectly, and they see some kind of dome as a function of filling. And well, the simplistic one-band continuum BCS theory prediction is very, very low, even for the real effective mass of the band. So obviously that's not the explanation, and then one can conjecture or speculate or propose that maybe there is quantum geometric contribution, so here there is some kind of scaling with the gap that matches, and of course our main message in these early works and also later is that everything scales like the gap in this geometric superfluid stiffness. So this is, in my opinion, still a very important thing to clarify, like really nail down with very detailed theory and experiment whether quantum geometry is there in TPG, but it could be. Okay, so that was the basics. And then I say something about some recent work. Some are very connected to this collaboration. So here, for instance, this is a collaboration of my group and Tero Heikkilä, who is also Simon's PI, and Dima Efetov's experiments. We have 2 papers, theory, experiment plus theory. And we wanted to go towards understanding that can you see these quantum geometry effects in Josephson-Jackson experiments? And for that, we considered, I first talk about the theory, this kind of junction where you have superconductor, normal metal, and superconductor, but now the normal part is a flat band metal. So not superconductor, flat band metal. And the existing theory of this kind of SNS junctions tells that, of course, there can be proximity-induced supercurrent. And the critical current of that supercurrent depends on Fermi velocity, and that should go to 0 in a flat band. So you ask, is the story there again boring, that you don't get any proximity-induced supercurrent? Well, we found out in the theory that there exists an interaction-induced current that has quantum geometric origin. So you need to assume that you have some interactions in this flat band, even when it's not superconducting. And then we get this extra contribution to the supercurrent, and it scales with the length scale here, this one, that is given by the integrated quantum metric. So it's basically the same mechanism that helps to have a supercurrent at all. It now helps the proximity-induced pairs to kind of propagate when there are interactions. And then in the experiment, one of the things that they observed was this, that they indeed had a twisted bilayer graphene piece between 2 superconducting leads, and the TPG was not superconducting, so it was proximity-induced supercurrent that they see here as function of filling this red curve. Sorry, which one? No, the blue curve, yeah. And then the red one is the normal state conductance. And typically in these kind of junctions, they follow each other. But here you see these are the dispersive bands, but in the flat band area, they don't. And then this interaction-induced current could be one explanation for that. We check the orders of magnitude. All right, then I tell about another work that was also done together with Tero Heikkilä and Guodong Yang, a postdoc from my group who was supposed to be here, but the visa process was slow for some reason. So he's not here, but I will highlight what he did. And here we consider the rhombohedral graphite like many, many others. You know, it's a great topic. And it has been already told here that there are surface states that are almost flat. And these flat surface states, they fulfill this ideal quantum geometry, that the determinant of the quantum metric is equal to the Berry curvature. And this result has also been derived by Andre, slightly different approach. So he calls it the Berry trash can. I would call our approach the Berry shopping bag because it's a bit more rounded. So anybody who wants to use this trash can method also see this paper, because it gives you a bit more, insight, because it's a slightly different approach. Anyway, but from that on, then we wanted to go to superconductivity and see how it behaves there. And the main message is that we, by looking at the superfluid weight, we saw that in this band structure, now we have used a displacement field to slightly open a gap. We can kind of understand this as a new type of or maybe it's not new, but for us it was new type of heavy fermion model where the heavy fermions actually have quantum geometry. So they are not like some kind of atomically localized heavy things. And then we have light fermions. This color scale is the quantum geometry. So of course here you have bigger, but you have here. And then comparison to Andrei's this TBG heavy fermion model. So there most of the heavy fermions are kind of don't have quantum geometry. So this is quite nice. This would contribute to supercurrent. Yeah.
Structure, which you have in twisted materials from the more rare.
Yeah.
Where does it come from in rhombohedral? What is the real space lattice that gives you a heavy fermion picture?
Well, maybe you should think that these are surface states, so at least they are localized on one surface.
But in the 2D plane, they are delocalized.
Yeah, they are delocalized. Yeah.
Okay.
Yeah. Okay, and the last advertisement is this work. So we have had already for a long time available in our papers the full formulas for superfluid weight for the S-wave. And of course, it's nice to have it also, important to have it for, let's say, nearest neighbor pairing, and you can find everything in this paper. And then we used it to look at some nearest neighbors pairing in Lib and Kagome, and it was quite nice. Here we saw some pair density waves which are not caused by nesting of any kind, but by quantum geometry of this thing. So you can have a look at the paper if you want. And yeah, Eli and Sofia are both here. Okay, then let's go to the new thing. So it's already late, last talk of the workshop, and you may be tired, so I will try to wake you up by asking you a quiz. So what do you think is the most frequently asked question from me? What question I hear the most often? Anybody can say if you... No? No, I never heard. This is the first time. But I give you a hint. You might ask it if I'm giving a talk and you are the chair of the session. Hmm? No, no. I tell you, it's how do I pronounce your name? So like millions of times. So I can tell you, it's Päivi, Törmä. It's very easy, and for a Finn, it's even trivial. But now comes the real thing. What do you think is the second most question that I... Yes?
5 minutes left in your talk.
No. No, it's related to this slide. Yes, what is it? No. Okay, so... Yes, what about this order? Wonderful, brilliant, Jana, yes. So 2015, I started to talk about this flat band superconductivity, quantum geometry. Always there was somebody really smart in the audience. What about this order? Because it's a good question. You know, you don't have any kinetic energy, so this order is also like immediately a big scale. So maybe all this very nice quantum geometry stuff just goes away with this order. So in the beginning, I answered all, well, it won't be a problem. And that was based on intuition and hope. But then, fortunately, some people did some numerics here. And they showed that it's not immediately destroyed. But I was not quite happy because I didn't understand why it's not immediately destroyed. So now, fortunately, Simons gave us some money. And we hired Christoph. He's our Simons postdoc, and this is a collaboration with Tero, with Simons co-PI. And we have now a very beautiful answer that essentially, I will explain what it is, but essentially, there is not much effect. And the superfluid weight change, when you have disorder, is controlled by localization functionals. So it's kind of beautiful, and it fits the numerics. But let's go to what we are actually doing. So we again use this wonderful uniform pairing approximation, but later if you do numerics, you can abandon that. But for analytical results, let's assume that the gap is the same in all the orbitals. And furthermore, we think that now that we have disorder, we have an effect that simply the gap could go down, but that's sort of a quantum geometrically trivial effect. And then we can have another effect which comes from the change of the wave function properties. So we focus on this one. And yeah, maybe this focus is kind of in line with Anderson's theorem, which says that at small disorder, this delta should be, delta should be rather robust to non-magnetic disorder. Of course, here we are kind of having strong coupling, but never mind, let's go ahead. And then we take known formulas from our previous papers. This is the flat band. This is now all in flat band. So this is a geometric contribution of superfluid weight, slightly different notation that we have used before. So gap, these are solutions of your whatever BDT theory, but it doesn't need to be now a block function because we can have disorder. So it's just a solution. And here is the current operator. Of course, everything in superfluid weight is related to current. And then we look at the this current operator is now expressed with the commutator. And then we look at the interband path, meaning that one of the states is in our flat band and the other state is in some remote band. And then we can approximate. We see that here the projector to the flat band appears, and this is nothing but a localization functional. So if you define the localization of your wave functions in this way, you have an intraband part like this and an interband part. So this interband part is here, and then it's delta squared over energy. This is number of unit cells. Okay, fine, we have this thing. And then a sanity check, let's now take the clean flat band. So then all these EA are just delta, and we obtain our old result. So of course, this I have been talking before the integral over the quantum metric over Brillouin sound, but that's nothing else than the interband localization functional. And here you see the definitions of these two localization functionals as defined by Marzari and Vanderbilt a long time ago. Okay, so let's then continue. And I show that's just the main result. And we now, this example is for on-site disorder, but we have done others. So you have on-site impurity with some energy, and you project to the flat band. And we get this result. The superfluid weight is changed by, this is the distribution, like width of the disorder distribution. You see that we have done perturbation theory because it's V over delta. So this is when the disorder is still weak compared to delta. And we see that it's just a difference between two localization functionals. And this PS is now the wave function of a single impurity. Yep.
Can I think of this as boron substituted for carbon? I'm trying to get a physical picture of what you're.
Yeah, I mean, of course, yeah, you could think about the impurity by substituting one atom with something else. Yeah.
That would be an on-site.
Yeah, yeah.
Okay.
Yeah. Yes, and then we checked it numerically for Lieb and Kreutz ladders. So the total superfluid weight goes down, but then when we look at how much does the gap go down, it goes like this. And then the superfluid weight divided by the gap, that's pretty much constant. So this tells that this wave function part of the change is pretty much zero. Kreutz ladder and the Lieb lattice. They are two lattice models where we tested these ideas. So I kind of interpret this in a way that this minus here means that indeed, when you introduce disorder, some of these nice interband effects that caused your supercurrent in the beginning, they are kind of suppressed a bit. But at the same time, you are breaking those interferences that made the flat band in the first place and inhibited motion. So that is this term, that something is going up as well. So therefore, the net change is small, and we are kind of arguing that this is in general small, but in these lattice models we can show that it's exactly zero, that these two localization functionals are actually the same. And now I think that there must be some kind of symmetry arguments and so on that tell when are these two functionals the same in general. And I think Jona could derive it on the back of the envelope before the end of the talk, but he doesn't have the envelope. So, but that's a nice thing to do in the future. And so but that's the basic qualitative message. We are safe that small disorder really doesn't destroy this flat band supercurrent transport. And this is one more numerical confirmation. We took the full numerics and then took this part, which is supposed to be the intraband change, and it really follows very nicely. All right, yeah?
Small. Would boron for carbon be small or large?
This I don't know, but small in my treatment means that it's small compared to the superconducting gap. That if you introduce energy scales that are much bigger than your gap, you would destroy it.
But chemically, almost any disorder, I would think, would be much larger than a tiny
standard
gap.
deviation that you study.
Pardon?
Standard deviation of the potential change that you study. So if you have
Yeah, no, understood, but the gap is tiny.
dilute
Yeah.
disorder.
Yeah, so if you...
Oh, you're averaging over space?
Yes.
Oh,
yeah.
that's a different statement.
Yeah. Sorry. I think I answered you incorrectly in the beginning. Yeah.
Or no, if I'm averaging over space, all is forgiven.
Yeah.
Okay,
Yeah.
gotcha. Thank
Yeah. Good. All right. So I go to the last topic. So I think it's really important to bring these concepts to real materials and check whether they make any sense, whether they are useful. And this is also an important part of this Simon's collaboration. You see there are other PIs, Miguel Marquez, his group, Theo is here, and Christian Haule. And from my group, the really heavy work has been done by Kaja and Martin, but Eli is also involved. Eli is here, Kaja and Martin unfortunately not. But anyway, so we thought that could we somehow combine these quantum geometry concepts to machine learning. So for that, we would need something that you can calculate from DFT data easily, and then see whether there are any correlations with anything that you would like to have, and then maybe use it. So first obvious thought is, what about the quantum metric? In principle, you can calculate it from DFT, but in practice it's horribly difficult, because this guy diverges enormously whenever two bands are very close to each other. So we neglected that one. However, then we thought that let's calculate this superfluid weight, this mean field superfluid weight that they have. And that can have serve different functions. Like it could be a proxy for the quantum geometry, because at least in flat band it's more or less the same. And it gives you superfluid weight. And once we have the machinery for that, we can also easily implement other possibly interesting quantities, like for instance the bound that Andre was showing, or whatever you have in mind, we can implement. And how we wanted to do this so that it's high throughput compatible, that a machine can do the calculation without any babysitting from a postdoc or even students, so no one-yearization. So these are the formulas. well known. And then you discretize the derivatives, and you can express them with quantities that you get from DFT, this kind of one-year function overlaps. So it's in principle straightforward. These red lines, however, contain a lot of work. It's not so easy to get it converged so that no human is needed, but we are more or less there already. So I show you just some examples how this, we have done them just for fun, how these look like. So this is MGB2. So yeah, the color is superfluid weight. And these are the geometric contributions. These are conventional. You see where it's typically everything bigger at the Fermi level. And what we see here, and many other usual superconductors, is that the conventional contribution is much bigger than the geometric one, which we kind of expect from this kind of highly dispersive materials. We have looked at some 2D materials, let's say twisted things and so on. There it can be big, but here it's not. Then also for fun, we looked at insulator, which this is not a superconductor, but you can use our formulas. And there you can see geometric contribution. It's this lower line. It can be similar or even bigger than the conventional one. So here the Fermi level is not touching any band, but if you assume some kind of hypothetical gap, superconducting gap, you see it. And apparently this one, although I think this is very atomically localized, it seems to hybridize with something and produces finite but very small quantum geometry. Okay, and then we made some sanity checks that does this give anything close to what you can observe. So calculated the penetration depth, and well, the order of magnitude is quite fine, but here it fails, maybe because this is type 2. Okay, so now I come to that's the end of my talk. And this is a speculation and also a question, because I have this great honor of having so many high TC experts here. So I wish that you will tell me if you think this idea is naive or stupid or wrong or already done, or maybe all four at the same time. So these are two celebrated relations, kind of universal relations to Uemura and Holmes, and they relate the superfluid state to something. And now, of course, when you do some kind of theory comparison to the experiment, you have to calculate ds somehow. And if you calculate it from determining what is the density of the electrons and the effective mass of the electrons, it might be wrong. Because there is this geometric part. So I'm not saying that it is wrong in any of the work done there, because there are two things. First, I think this first one is the more important. It might be that this part is very, very small for all of these materials. But, okay, we don't know. I mean, we will check soon, but this is one question. Second thing is that, of course, if you take calculate ds from some linear response thing with full theory, without doing approximations, without throwing other bands away, you will include the quantum geometric contribution, even if you don't know. But I have seen at least some papers use this simple relation. So that's really a question to you. I welcome comments whether we should forget about this or whether we should revisit something. Okay, so I'm on my last slide, and I would like to present my personal vision of this collaboration. So I think we should really focus on the very fundamental open questions that have broad significance. And when choosing the systems to study, because you always then need something concrete, it should be either something that is very like exceptionally well described by theoretically, or it can be controlled experimentally better than other systems. And then I'm promoting very much this material search aspect, And there we should not sneer at conventional superconductivity because it's the place where we can test AI, basically, because we can calculate things with DFT. And in this material search, we should not be focused on TC only. There should be really big emphasis on whether it's synthesizable, ductile, high critical fields, and so on, because in that way we can produce something that really revolutionizes our technology and also makes the experimentalist much more happy. So, and then we have to go to unconventionals. Already Miguel was mentioning this. And first maybe some, I don't know, correlation or similarity approaches. And there, for people who are doing some kind of numerical or other calculations for unconventionals, now the thinking here is that you don't need to be so accurate with TC. Factor of 2 would be fine for this kind of things. Because if you propose something 50 Kelvin, it turns out to be 100 Kelvin, the experimentalists don't complain. So, but this, whether it's synthesizable, ductile, high critical current, I mean, at least synthesizable is very important. Yeah, and I think, well, I hope AI will develop. I cannot do this myself, but obviously we are not yet at the point where these LLMs are very good at kind of out-of-the-box thinking, producing something that doesn't match your distribution, but is still meaningful. But humans can sometimes do this, so I think we can teach the AI to do it with time. And this is my thing that we should, to some extent, avoid. I mean, I understand the intellectual fascination with exotic superconductivity and rich phased aircraft, but you know, this usually means also many parameters, and then you can fit all kind of theories. And if we want to solve the main open questions, maybe we should not completely get into this rabbit hole. And yeah, then this business as usual is in collaborations. It often happens that people kind of don't do anything else than what they would have done if they got the money individually. So we really have to avoid this. And we wanted to invite Igor Masin here. He could not come. So I just want to highlight his paper. It's a banger. You should read it. So inverse Occam's razor means that if there are several theory explanations for a particular experiment, you choose the most complicated and more fancy one. And this, of course, we should avoid. So with this, I would like to thank you for your attention.
Jan, please.
One number, right? Yeah. So you have a value for all the states in the mass structure. What would be the strategy? So you integrate over a window? Or?
Yeah, you see, this, for instance, superfluid weight, it's an integral over all energies and K values. So that's one number.
Ah, okay, that's one number.
Yeah,
okay.
It's just for visualization. I saw the band structure.
Okay.
Yeah, we can get it if that's somehow useful, yeah.
Yes. I mean, for the disorder part, have you considered a case that your system become critical right at the metal in student phase transition? If you crank up disorder, your wave function are multifractal. And there are some works that multifractal T potentially can enhance superconductivity. I'm trying to see whether quantum geometry can say something.
Yeah, we have not considered that, but it sounds like an interesting thing, yeah.
Yes.
Okay. Thanks for the talk. That I would actually like to combine the two main topics here and kind of point out that if you have disorder in the conventional case, also the superfluid weight is changed, and then you can also study what is the geometric contribution in the disordered case in the conventional case, and you find out that actually disorder enhances the relative contribution of the geometric contribution. So if you would do your kind of these estimates in the disordered case, I think you might actually get relatively larger contributions.
Yeah.
In this, and then also for this high TC story, I think this maybe the question is also in the disordered limit, at least weakly disordered limit.
It's not weakly disordered.
Well, but in the sense that let's say if it's a D wave, still.
What over? I mean, what over tau is bigger than the gap.
Yeah. Okay. So it's then strongly disordered. Yeah. Yeah.
Antoine?
Very nice talk. Can you explain why you want to stay away from rich phase diagrams? I mean, I would imagine then once you go to a conventional superconductors, often interesting things are found in materials that do have.
Yeah.
So aren't we shooting ourselves in the
I'm not against, like, if it happens to be rich, why not? But I would rather, like, can you find a simple phase diagram that is really related to a genuine open question? Because then if you have just, let's say, two competing phases and you don't understand how they compete and so on, so in that system, because it's so simple, you would have less parameters. So then the possibility of true understanding is bigger. So that's what's my point.
I certainly agree with that.
Yeah.
I mean, it makes for conceptual simplicity, but on the other hand, I think it is really a defining principle.
with strong correlations that they have rich and complex phase diagrams with competing or intertwined phases.
Yeah, yeah.
And so there is some richness and opportunities for control there.
Yeah, yeah.
So I don't think we want to cut ourselves from.
No. I would let's say the poorest among the rich, right?
The cuprates are simpler part of that. But these diagrams with the like the 2D materials, which are very beautiful but very complicated. I think that would be the. It's too many.
Yeah.
Very beautiful. But Steve and then.
Yes.
So is the size of the superfluid density comparable to the dispersion of the quasi-particles, or are these really separate effects?
Yeah. So
Could I think of it in some normalized sense as being, ordinary superfluid density just with these highly renormalized quasi-particles?
no, it's not this one. So if you think about just the renormalization that comes from simple Hartree, so at least in many of the toy models that we have looked at, this is for small interactions much smaller than this effect provided by quantum geometry. So they are two different effects, and it's of course there, but at least there are many models where the geometric one is much bigger than the Hartree. Then I don't say anything about if the renormalization comes from strong correlation, what happens.
So, comment and a question. Comment, for your list there, you have synthesizable ductile high critical current. Get rid of ductile. No, in the sense that a lot of applied superconductors are not ductile. That's something the community knows how to handle. If you really limit yourself to ductile, you're shooting yourself in the foot. MGB2 is not ductile.
No. Okay,
No.
that's maybe for
Right.
applications, right? Or?
MGP2 is applied.
Okay,
Right,
good.
right.
We can get rid
Right.
of
No,
it.
so you get rid of the other one is high critical current. I would deeply urge you to look at upper critical field. Critical current is extrinsic
Yes.
and it's outside your purview.
Yeah.
Right. So that was the comment.
Yep.
Question. In Andre's talk, he mentioned that lambda quantometric for MGB2 was large. So quantometric played a role. In your analysis, the quantum geometry had no effect on MGB2.
Yes.
I'm confused. It's probably because I don't understand a nuanced distinction.
It's because I should have actually mentioned that.
Okay.
Very good idea.
Thank you.
I have only talked about how quantum geometry affects the superfluid stiffness. And there, indeed,
Stiffness or density?
Stiffness, density, weight, that's
Okay.
all the same.
All right.
Yeah, superfluid density, if you wish. But Andre has studied another thing, how it affects the electron-phonon coupling. And in MBG2, it happens that it has a huge effect on electron-phonon coupling, but a very small effect on the superfluid stiffness.
Interesting. All right.
Yeah, and that's why also we think that if we somehow can probe the quantum geometry, even in a very dispersive bands, hopefully it could tell something about electron-phonon coupling being large. Yeah.
Those two questions. One is comic question. How exotic should be exotic superconductivity to stay away from it?
Well, if you need below millikelvin temperatures, sorry, below 100 millikelvin, yes.
Okay, so it's temperature essentially.
Yeah.
And second, more serious question. Correct me if I'm wrong, but I thought that you were also alluding that even in cuprates, there may be contribution from quantum geometry to stiffness. And is there any indication that there is a reasoning for this? Because normally it's just one orbital, one band, and Andrea is shaking hands, so it's probably not.
Yeah, I mean, people have done this one orbital, one band approximations without knowing that the other bands might be.
Yeah, but there is a Jean-Reich singlet, it's normally 5 electron volts, so. And? Okay.
Yeah, in one of the cubes.
Yeah, so it's a question about 1% corrections.
Well, in one particular material, but we don't know in general. I think it's still open. I mean, it might be small, but it's open, I would say.
I was wondering, in these flat band superconductors, this must be a very dumb question from an experimentalist, but is there a specific length scale that characterizes this superconductivity in the absence of VF? And when you discuss disorder effect, second part to the question, when you discuss disorder effect, how does the length scale of the disorder, on-site disorder center interact with that, whatever characteristic length scale is associated with that?
Yes. So the typical length, let's say the Cooper pair size or whatever, it's related to quantum geometric quantities. It's essentially given by this quantum metric times lattice constant or something like this. And here, well, we studied on-site disorder. Of course, the size of the bound state, that depends on your quantum geometry. So the same length scale is there in the bound state wave function and the Cooper pair size. And this maybe is behind this, that it doesn't have much effect. But what we assumed is uncorrelated disorder. Of course, if you have correlated disorder, things can change also with length scale.
If I were to have, experimentally, it's okay to control W, but it's also okay to control disorder density. If I were to draw some back-of-envelope expectation, how should I expect the superconductivity gets killed as a function of the disorder density instead of the size of W?
Yeah, so certainly when, let's say that if your impurities somehow interact, and then if you can calculate or evaluate the size of the impurity wave function, so if they start to overlap, the impurity wave functions and the impurities are interacting, then of course I think many things would happen.
Compared to that impurity length scale?
My guess at the moment is that the length scale is similar for the impurity, on-site impurity and the Cooper pair.
But I thought the impurity density is something we can control experimentally, but the flat band is given in that system. That's non-negotiable.
Yeah.
So then shouldn't the length scale of the Cooper pair be a fixed thing, while the impurity density is something we can control?
Yeah, this is true, yeah.
Okay.
Yeah, you can control the density, and things would not change unless when you go to very dense impurities, because they start maybe interacting.
Done. semi-infinite experiments of doping superconductors, seeing how they're affected, whatever. If you have these rather exotic superconductors coming from this quantum geometry, okay, would, you know, Abrikosov-Gorkov spin flip scattering be weakened or be changed? You know, this is a very standard impurity perturbation. That might be interesting. Has any thought been put in? And then again, it goes back to the question of what do you mean by weak impurities? Because when I play that game, thulium is a weak magnetic scatterer because its de Gennes factor is low. Gadolinium is huge. So there is actually a parameterization of the impurity, not the density. So, you know, are there implications like that? Or are these things to consider? Because they might be very interesting experiments if you ever find a system that would host it.
Yeah, we didn't look at that, but I mean, we have a little bit of things about Andreev scattering and so on in flat bands, but not this one. So we should look at it.
Because I mean, it's going straight into your impurities, but now we're starting to interact with what flavor of impurity. And experimentalists, depending on the system, have quite a palette to paint with.
Okay.
Doped bismuth selenide, doped topological insulator, and we have shown exactly that depending on the symmetry of the impurity distribution across the pentopole layers, that is also associated with how the orbitals are distributed and the topological aspects in the system. The density distribution will change, you know, how often these impurities will be found symmetrically or antisymmetrically across those layers, and that evolution of the distribution with the symmetric and antisymmetric contents changes the expected Abrikosov-Gorkov curve qualitatively.
Okay.
Yeah. For example, so there is at least one example.
This order can be a good probe to understand this system.
And a tractable one.
Yeah.
I wanted to make a last comment. I'm sure it's well known, but maybe it's worth repeating related to the conversation between Andre and Päivi. So in one-band models, tight-binding models are, of course, approximations to continuum models. One-band tight-binding models have zero quantum geometry of the tight binding, but the underlying orbital that you have projected that tight-binding model on will have quantum geometry, and that all is captured if you do the quantum geometry from the con-sham. So just because you've done a one-band model projection doesn't mean you don't have.
Oh, sure, absolutely. The question, the question only is how big is the effect.
That's right.
How far are the modes?
Yeah, exactly.